Hello, my name is Sujay. I'm a senior at MIT double majoring in math and physics, and I'm applying to the mathematics PhD program at the NYU Courant Institute. I chose Courant because its professors span the gamut of physical applied math, and that breadth will enable me to find the research areas in which I can make the best contributions. Two of the things I prize the most about math are its ability to find connections between areas that may seem unrelated, and its ability to offer insights into important problems in other disciplines. I chose Courant because its research exemplifies the best of both. Charles Newman's work connecting statistical mechanics to the Riemann hypothesis, and Daniel Stein's recent work on a mathematical framework for belief dynamics in psychology are just two examples that show the best of mathematics in my eyes, and confirm to me why I'm putting Courant at the top of my list. I think I'm a good fit for Courant because my intellectual interests are similarly broad to those of the Institute. Although my primary mathematical interest is in its applications to fundamental physics, I do take an interest in politics, sports, and a number of other areas, and I'm always looking for the places where math can offer a fresh perspective. As just one example, whenever I watch an NFL game and the announcers bring up some correlation among the multitudes of available statistics, I'm always thinking to myself, what might be causing this? Is this really meaningful? With my background in pure math, applied math, computer science, and physics, I'm confident that I can perform impactful mathematical research in any discipline and fit in perfectly with the intellectual atmosphere at Courant. One of my favorite ideas in mathematics is the Bertrand paradox, which I will illustrate to you using this problem, which says, suppose you choose uniformly at random a chord of a circle. What is the probability that the chord is longer than the side of an equilateral triangle inscribed in the circle? So for instance, these segments are bad, these segments are good. I will show you three different methods of doing this problem. For the first method, we will choose 2 points uniformly at random on the circle. Without loss of generality, let's say the first point is the one on top, and let me draw an equilateral triangle for reference. Then it's clear that the second point will give us a chord that works, if and only if it lies in this 120-degree arc right here. And that occurs with probability 1/3. For the second method, what we will do is we will pick a random radius, doesn't matter which one, and then we will pick a random point on that radius at which to draw the perpendicular. Now when does this work? It turns out that this chord will be longer than the side of the equilateral triangle, if and only if the point you chose lies within the inner half of this radius, and that occurs with probability 1/2. Well, that doesn't look good, but let's make things even worse with the third method. And for this one, what we will do is that we will pick a random point inside the circle and then use that as the midpoint of the chord, which will then uniquely define the chord. And when does this work? It turns out that it works if and only if the midpoint we chose is within r/2 of the center of the circle, and that occurs with probability only 1/4. So look at this. We just used 3 different methods and got 3 different answers to the same problem. So what does this mean? Basically what it means is that ordinarily the notion of a uniform random choice is completely unambiguous, and we can describe it using something called a principle of indifference. So for example, if I roll a standard die, all the faces are identical, so I can assign the same probability to each one, namely 1/6. But it turns out that here we have a problem that's complicated enough that we can create 3 different notions of what uniformly at random might mean, that all of which are not obviously illegitimate. And this is the essence of the Bertrand paradox, which basically says that in a domain of infinite size, the principle of indifference may not produce a single well-defined notion of a uniform random choice.